Hi guys, and welcome back to my channel. In this video I want to talk about resonance, and this is a topic you might be familiar with from AP Chem or general chemistry course, but I sort of want to talk about it a little bit more in depth and a little bit more in the context of organic chemistry. So just to recap, we know that resonance happens when one Lewis structure does not completely describe our molecule or our ion, right? So we need this sort of blend of different Lewis structures to describe our molecule. How resonance can help in organic chemistry is because based on these resonance structures and which ones are the most sort of prominent, which ones really contribute to the actual structure, we can see which atoms have high electron density or low electron density, and this can affect the reactivity of different molecules. So let's just get right into it. Okay, so this is just an intro to resonance, so this should be very familiar from AP Chemistry. It's basically when one Lewis structure does not adequately represent the molecule. And we can see this with the nitrate anion, we can see this with the carbonate anion, and there's a bunch of other, molecules where one Lewis structure does not completely represent something, and we need this blend of different Lewis structures. So we can see with this nitrate anion, if we look here, we have this nitrogen bonded with 3 different oxygens, and only one of the oxygens has a double bond. But which one of the oxygens have the double bond is, arbitrary. We could have the double bond be connected to the top oxygen right here, or the bottom right, or the bottom left. And you can see these arrows I've drawn, right? You might be confused as like, what are those arrows? Basically what I'm doing is I'm using the arrows to show electron pushing. So you can see that I'm taking this electron pair, I'm pushing it to form a double bond, and I'm taking the double bond where the nitrogen was connected to the other oxygen and moving it to a lone pair on that other oxygen. So this sort of language of using arrows to denote electron pushing is really useful, and one that I will be using later in this video as well, especially with organic structures. So just sort of, I guess, just understand what I'm doing in this. I'm taking an electron pair, moving that electron pair to form a double bond, taking the electrons from the double bond and pushing that to be a lone pair. That's all I'm doing. Okay, so the molecule is instead a hybrid of many Lewis structures. And what exactly does that mean? Let's think of an analogy. And this is an analogy that Klein gives in his organic chemistry book. It's a really good analogy. I thought it was very useful. It's basically like a nectarine. A nectarine is a hybrid of a peach and a plum, right? It has features of both a peach and a plum. But it's not like a nectarine is flipping between being a peach and a plum, right? So we have a nectarine, it's just a nectarine, right? It's not like 1 second it's a peach, the next second it's a plum. So just like that, with our nitrate anion, it's not like 1 second it's this Lewis structure, the next second it's that Lewis structure, right? It's a hybrid of all these Lewis structures. So that's just something to keep in mind when you're thinking about what resonance structures actually are. So one point I want to make is that if you were asked, right, what is the which is the shortest nitrogen-oxygen bond in the nitrate anion? All of these nitrogen-oxygen bonds have the same length. Why? Because remember, it's not that 1 second it's this guy, the next second it's that guy, right? If it was like that, the 1 second where it was this guy, our double bonded oxygen would be a shorter bond because double bonded are shorter than single bonds. But remember, it's a hybrid of all 3 of these. So if we look at these, right, each Lewis structure is basically equal in terms of how much it contributes because they're basically the same structure, right? It's equal in terms of its contribution, and each Lewis structure has the double bond to a different oxygen. So all of these bond lengths are going to be the same. It's going to be in the middle of the length of a single bond and the length of a double bond, because it's not a true single bond because, one of these Lewis structures has a double bond to that oxygen, but it's also not a full double bond because there's 2 of these Lewis structures that don't have a double bond to that oxygen, right? So our NO bond lengths, this is just something important, are all the same. And this is, if you're able to tell this, right, that means you truly understand what a resonance structure is. It's not that 1 second it flips between this one and that one, it's that it's a hybrid of these structures. So again, our nitrate anion is a hybrid of these three structures. All bonds in nitrate are the same length, as all structures contribute equally and they have the same energy, right? And that's because all of these structures are essentially the same. You have a double bond to one oxygen and two single bonds to the other two oxygens. This is really important. Electrons participating in resonance are delocalized. Why are they delocalized, right? Because we need to be able to push these electrons around. Remember how we were doing electron pushing here? The reason we're able to do that is because they're delocalized. If they were localized, we wouldn't be able to push them around. They would be localized, they would be staying in their space. But they're delocalized instead, and the electrons participating in resonance are delocalized, which means that we can, quote unquote, we can push them around, we can do electron pushing. We can take a lone pair and make it into a double bond. Because remember, double bonds are formed by what? They're formed by the overlap of p orbitals. So a double bond is basically p orbital overlap, side-to-side overlap. And the only way we can form a double bond from a lone pair is if that lone pair was not in a hybridized orbital, but was instead in that p orbital already. So basically, this overlap can form if the lone pair is in a p orbital already. So what the point I want to make with this is that delocalized electrons must be in p orbitals rather than localized hybridized orbitals. So basically, an electron that's participating in resonance cannot be in like an sp2 orbital or an sp3 orbital. It needs to be in a p orbital. It needs to be delocalizable. So this is a huge effect for determining molecular geometry. And it's for this reason that amides are planar. So let me draw an amide and we can actually see, right, why that's happening. What exactly is an amide? So I'm going to use a bond line structure, or, actually I won't use a bond line structure this time. But, right, we have basically something like this, where we have two R groups coming off our nitrogen and an R group coming off our carbon, connected, double bonded to an oxygen. And we have a lone pair on our nitrogen. Okay, so we can see that we have some resonance that can happen here. I can push these electrons down to form a double bond, and I can push these electrons up to form a lone pair, right? The double bond, the carbonyl double bond, can go and form a lone pair, and that resonance structure would look like this. We would have CO bond with a negative charge and a positive charge on this nitrogen. So hopefully this makes sense. I just pushed the electrons around. We'll go over rules for electron pushing later in this video. So why is this planar, right? That electron that participated in resonance was in a p orbital. So if we remember that, right, we had this nitrogen that had an electron pair. This lone pair is in a p orbital. And we have three other sort of electron domains. We have three other groups coming off of this nitrogen, which means that we have sp2 hybridization. And this means, right, with our sp2 hybridization, this means that it's planar. And our delocalized electron is in a p orbital. So this is really, really important, right? It's not that our nitrogen is sp3 hybridized with our electron in an sp3 orbital and our three other groups in our three other bonding, orbitals in sp3 orbitals. We have sp2 hybridization with the p orbital that has the electron pair. Okay, so that's something really important to remember, and it's used a lot in organic chemistry. Let's just go to the next slide now. So these are the two commandments of resonance, things you can never do, okay? So first commandment is you can never break a single bond with resonance. Otherwise, when you break a single bond, you're basically breaking the structure. So I drew these with bond line drawing, and just with bond line drawing, every corner, every vertex is a carbon, and you assume that there's enough hydrogens on each carbon such that you have 4 bonds to each carbon. So if I drew, ethane like that, there's 2 vertices, there's 2 sort of, start and end points. Here there's 1, 2, 3, 4, 5, right? In this example that I drew, there's 5 carbons. So with ethane, right, this is ethane, and that's the same thing as if I drew 2 carbons, and then you draw as many hydrogens such that each carbon has 4 bonds. So you would draw 3 hydrogens on each carbon. But this is just a much simpler way to draw stuff, so I'm going to stick with that notation, right? Okay, so let me just erase this, and let's go to this. So you can see here, right, in this first example that I gave, we're breaking a single bond. We're taking the electrons in this bond and we're moving it over to form a double bond, right? That's not a resonance structure. Now at this point you've broken the, you've broken the structure into 2 different molecules. That's not resonance. The molecule is not a hybrid of 2, smaller molecules. So you can never break a single bond with resonance structures. The next one is you can never break the octet rule. So the octet rule basically means that carbon needs to have, or any small atom, right, nitrogen, oxygen, carbon, those sort of key atoms, can only have 4 bonds, right, max, because they can only have 8 electrons total. And they can have less than 8 electrons, that's possible, but they cannot have more than 8 electrons because they don't have d orbitals they have access to. And because they don't have d orbitals they have access to, they can only have 8 electrons and 4 bonds total. Okay, so we can see here that with our oxygen, we have a negative charge on this oxygen, and our resonance structure, our fake resonance structure that's wrong, is this, right, where we have a double bond, and now we've sort of pushed our electrons to form a double bond. But remember that we had 2 hydrogens here before, right? Because each carbon, it's implied that there's 4 bonds. So now we have 5 bonds connected to that carbon. This is wrong. You can never have 5 bonds connected to a carbon. You can never have more than 4 bonds on a carbon, because carbon does not have d orbitals that it can use to hybridize and form bonds. Okay, so those are the 2 rules you can never break with resonance structures. Now let's go to the next slide. I'm just going to talk about things to how you can recognize when there's a resonance structure, especially for organic molecules. So here's some patterns, and to really get the hang of resonance structures, you just have to do a ton of practice. But I think these are good patterns just for a beginner, so you can recognize these patterns and just immediately apply them. So the first pattern is if we have a lone pair next to a pi bond. You can see that here we have an ester. This is an ester functional group. Ester functional group. And we have a lone pair on this oxygen. And we have a pi bond from the carbonyl pi bond. We can push this lone pair to form a double bond, and we can push that pi bond to form a lone pair. And we form this resonance structure. So you can see we recognize there's a lone pair, there's a pi bond, they're next to each other, and we can automatically sort of apply this way of moving this way of pushing electrons to find the next functional group. And you should remember that this is basically exactly what we did with our amide resonance structure. If I just redraw it, we had something that looks like this. We had 2 R groups, we had our carbonyl, right? And what we did was we took this lone pair, we pushed it, and we had our pi bond, and we pushed that to form a lone pair. So this is the same exact thing that we just did. And just like, the amide, this oxygen, this ester oxygen, because this electron pair is participating in resonance, that oxygen is sp2 hybridized. Because remember that the delocalized lone pair is in a p orbital and not in an sp2 or sp3 orbital. The next pattern is when we have a lone pair next to a carbocation. And what is a carbocation? I'll talk more about this in a future video. A carbocation is just an electron deficient carbon, right? It's a cation. So it's electron poor, right? And what this means is that our carbon has only 3 bonds instead of 4. So when I draw this, because it only has 3 bonds, it only has 6 electrons. So it's not breaking the octet rule, but it doesn't have a full octet, which means that the carbon is unhappy. So like if we look at number 2, this carbon here has a positive charge, so it only has 1 hydrogen coming off of it. It only has 3 bonds. So how can we draw resonance? When we have a lone pair next to a carbocation, we can push the lone pair and form a double bond, just like what is shown in the drawing, right? We just push the lone pair and form a double bond. And remember on the previous slide we said, oh, you can't break the octet rule, right? And we drew a negatively charged oxygen just pushing the lone pair and forming a double bond. Why can we do that here? That's a good question, right? Why can we do that here? We can do that here because the carbon initially was electron deficient. It only had 6 electrons. So now when we push the electrons, we're giving the carbon 8 electrons, which is an octet. So we have not broken the octet rule. We haven't gone above 8 electrons, and that's what's important, right? We can push it because originally we had a positively charged carbon. We had an electron deficient carbon instead of a happy, octet carbon. So that's the difference between this example and the example I gave on the previous slide. Let's look at the third pattern. We have a pi bond next to a carbocation. And just like how we had a lone pair next to a carbocation, with pi bond next to a carbocation, we just move the pi bond such that our carbocation is now, becomes not a carbocation and has, because we're taking electron density from the pi bond, moving it to the carbocation. So here we have this pi bond, we have our carbocation at the left, on the left carbon. We can move this pi bond over to the left, and notice that we're taking electron density away from this right carbon, and we're giving it to the left carbon. So what we're doing is, so our right carbon is going to end up with a positive charge. Our left carbon is now going to be neutral, which is what we see in this image, right? Now let's look at number 4. Pi bond between 2 atoms where one is electronegative. And this is a pretty easy example, right? For example, take a carbonyl. We have a CO double bond. Oxygen is very electronegative, so it has a negative sort of delta charge. Carbon is much less electronegative than oxygen, so it has a slight positive charge. If we have this pi bond in between, we can have this delocalization that goes on. So I can draw the pi bond just, being pushed up onto a lone pair of the oxygen. And so I have, because I took electron density away from the carbon, I have a carbocation, but I gave electron density to the oxygen. Now that's an anion. The oxygen has a negative charge. So this is just a really simple, resonance structure with carbonyl groups and other groups where we have two different, two atoms that have a big difference in electronegativities. The last pattern I want to go over is when we have pi bonds going around in the ring. And you might have seen this in AP Chem where you have benzene and you can sort of just shift all the pi bonds around in the ring. So here we have benzene, right? And we can move these pi bonds around in a circle to form this other resonance structure which is just this, I just shifted all the pi bonds in one direction and we form, another resonance structure. So with pi bonds going around in a ring, we can easily form a second resonance structure. So these are 5 patterns that are good to keep in mind, and when you do more and more problems, it'll get easier and easier to recognize these patterns. But it's very, I don't recommend memorizing these or just trying to cram them in your head. What I recommend doing is solving a ton of these resonance problems and you'll recognize, oh, with this functional group, I gotta worry about this pattern. With amide functional groups, I gotta worry about lone pair next to pi bonds. With ester functional groups, I gotta worry about lone pair next to pi bonds. With aromatic functional groups, I gotta worry about pi bonds going around in a ring. With carbocations, I gotta worry about lone pairs next to the carbocations. Stuff like that. You'll find these patterns really easily, and once you do enough of these problems, it'll become much quicker and much easier. So now I just want to give a little quick example problem. It shouldn't be too difficult. Here we have a benzene derivative. We have aniline, and aniline is just, we have our benzene sort of ring, but we have an NH2 group coming off of it. So you might immediately notice that we have a lone pair on the nitrogen, and we have a pi bond, right? So this is lone pair next to a pi bond, exactly that. So if you remember what we did, we pushed the lone pair to make it a double bond, and we moved the pi bond, up. We move the pi bond on to become a lone pair. So we get the structure that looks like this. We have a negative charge on the carbon, and we have our positive charge on the nitrogen, right? Because we took the lone pairs from the nitrogen, pushed it to make it a double bond, and then we took the pi bond electrons, pushed it to make it a lone pair. That's exactly what we did with amides, exactly what we did with esters. Now, if you notice, there's still more resonance we can draw. We have a lone pair next to another pi bond. So let's do the exact same thing over again. And now we formed another resonance structure really easily, right? We just did the exact same steps. We pushed the lone pair to become a pi bond, pushed the pi bond to become a lone pair. And we get this structure. And now we have another thing we can do. We have a lone pair, we have another pi bond. So there we go. So it's gonna take a while to draw it out, but you can see that we're just doing the same thing sort of like 3 different times, right? We're doing basically the exact same thing. And finally, we can push this around and make it, again, what it was sort of like before, except now all our pi bonds are just shifted around the ring. Okay, so you could also have gotten this resonance structure from the first resonance structure by looking at our 5th pattern where pi bonds in a ring can just shift around, right? But we did it, shifting it one by one. Okay, so what is useful about resonance in this case? I'll just give a little taste of why this is important, right? So this group here, our NH2 group, because we have a lone pair on our nitrogen, we call this an electron donating group. And why do we call it electron donating group? It's a little bit self-explanatory, right? We have lone pairs on our nitrogen that can be donated into the aromatic ring. And how did we do that? We took this lone pair, we made it a pi bond, and we took the pi bond and made it a lone pair. So essentially what we've done is we've taken the lone pair from the nitrogen, we've taken the electrons from the nitrogen and put it on a carbon. We put it inside the ring. That's why we call it an electron donating group. So why is this important, right? You might be asking. Why is this important? This can activate the ring to all sorts of reactions. So can activate the ring. And what do I mean by activate the ring, right? What exactly does that mean? Activate it to what? So this, right, because we have a resonance structure where we have negative charges on carbons. So with the negative charges on carbons, what that can act as is a nucleophile. We have regions of high electron density inside our ring, inside the ring. And these regions of high electron density wants to attack regions of low electron density. There's this sort of charge attraction, right? So when we have high electron density, it wants to attack regions of low electron density and react, right? So that's just a taste of why we use resonance structures, because we can see immediately from these resonance structures that our NH2 group is going to activate the ring. Why is it going to activate the ring? Because it donates electrons into the ring, and that will cause, reactions to occur. What sorts of reactions? Especially reactions where you have a nucleophile or a place with high electron density attacking a place of low electron density. Okay, so that's all I wanted to really cover in this video. Hopefully this made sense, and I hope it was informative. Thank you guys so much for watching, and I'll see you in the next one.